Okay, so we start with the lecture 36. So in this lecture we are, so as far as our lectures have been concerned, mostly we have been dealing with the different forms of stability, all associated with a still water line. Now by still water line I mean a water line that is horizontal, not it does not have to be horizontal, but it is straight. So the water line is okay, it is always horizontal. So the water line, when it is horizontal, we have we have already devised the set of equations that will deal with the stability of ships in such a horizontal water line. For instance, we deal with the heeling. We have dealt with all the problems associated with heeling that is happening again in case of a still water line, or what we call as a horizontal water line. And now another possibility exists, which is the actually the reality in seas, in most kinds of seas, that is the presence of waves. Now waves, for since you are the beginning of naval architecture, you might not have had much of an exposure to waves, but waves is an important phenomena when it is associated with ship motion. Mostly we are talking about waves that occur on the surface. Now you know that when we are dealing with the ocean, we have the interface between the ocean and the air, that is you have that surface part of the water. So that interface which divides the water from air, that interface we call it as a free surface. Now as you imagine, as you must have seen in the shores and even in deep seas, there will always be some undulations of the free surface. It is not a horizontal plane, but it is a undulating time dependent unsteady transient phenomenon. That free surface is a transient surface, it varies with time, it is unsteady. Now the consequence of such a unsteady surface or a wavy surface, as it is, that waviness is due to the presence of these free surface waves. Now almost all the waves that probably not all the waves, but most of the waves that we are dealing with here are dealt with, are associated with the free surface waves. So we deal with, so there is in naval architecture a broad category of waves in which we deal with free surface waves. These are the waves associated with the free surface. Then this is not that important in naval architecture, but in oceanography we come across another type of waves that are associated, that are called as internal waves. Then of course there are even this free surface waves, there are different kinds: gravity waves, swell, wind waves. Of course gravity waves are mostly generated by wind only. So these different kinds of waves exist, and when you go down into the region below the surface where there is a density gradient, this is not part of this course, but you will see that when you go down in the ocean, after a region in the top region of the ocean, there is a region very close to the surface for about 50 meters. There is a region where the density is uniformly distributed, you have very little gradient in density, or there is no density gradient. So that we call it as a mixed layer, and there is a region below that where there is a not very strong, but a fairly good gradient in density, that is in that region the density continuously increases with depth. So as you can imagine, density has to increase with depth, because only then the system will be stable. If you have a less dense fluid lying above, if you have a high dense fluid lying above less dense fluid, as you know, the system will be unstable and it will produce circulation, and the whole thing will actually become totally unstable. Now that is a different system. So this region inside where there is a very strong density gradient, you can have internal waves. These are the waves that are generated due to this density gradient. So different kinds of waves exist. We in this naval architecture only deal with what are called as free surface waves. Now because of the presence of these waves on the free surface, you will see that the ocean surface is always not even, it is not a horizontal line, it is not a line as such, it is a curve. So, that free surface is a curve, some function. So, you get the free surface eta as a function of x, y and t. So, this free surface, or this is what we call as the elevation. Elevation, by elevation we mean if this is the free surface, if you consider this to be a still water level, this or this are called as eta. Here eta is positive, therefore, the surface of the water is above the mean water line or the still water line, and in the second case the eta is negative, as a result of which it is below the water line. So, this is eta is an elevation which is a function of x, y, that is a horizontal distance and time, it varies with time. So, this is known as this is the effect of waves on the free surface. Now, as a result, what will happen is that if you have a ship, like this, now all the problems that were considered, all the problems that we considered till now included a water line like this or like this. At any case, it is a horizontal water line, and as you know, even though I have drawn this as slanted, it is still a horizontal water line. It means that the ship has tilted. So, the ship has tilted by some amount or trimmed by some amount, as a result of which you have got the which is represented by a tilted water line. Now, this is the type of water lines we have been considering till now. The different types of water lines, whatever we have considered, even if you are considering healing also. So, if you remember, we have considered different types of healing problems. All those problems we considered so far dealt with water lines like this, like this. So, always it is a straight line. We never dealt with any kind of problems where we have water lines that are in anything other than a straight line. So, this is the problems that we have considered till now. Now, we come to this new type of problems. As I just told you, the presence of waves makes the free surface a tilted, makes it a curve instead of a straight line. So, it becomes like this, it becomes a curved surface instead of a straight line, and therefore, your water line really looks like this in the presence of a wave in a free, or in the presence of the effect of, in the presence of the real free surface. Please note here one thing, I have used the term free surface or the free surface effect in actually I have used that term here 2 times. In hydrostatics, there is a free surface effect which we have already talked about, which is the effect of free surfaces on free surfaces of liquids, means it is the effect of tanks. So, if you have tanks inside the ship and you have a free surface, that means if the tank is not fully filled and the surface is free, you know that the surface can tilt, and if the surface tilts, that effect and the effect on GM is called as a free surface effect. This chapter, this lecture today, the free surface I am talking about has nothing to do with the free surface of tanks. That what we called as a free surface effect so far, they are totally unrelated. There is no relation between the two. This free surface effect, or this is associated with marine hydrodynamics, the wave hydrodynamics. The hydrodynamics call it also as a free surface effect, but please discern the difference between the two very clearly. There is no relation between the two free surface effects, that one is different, the other one is totally different. So, this free surface effect. So, what we are saying is that as a result of this free surface effect, so all the free surface effects we are talking about in today's lecture are concerned with the air water interface and waves. It has nothing to do with tanks, no such, do not bring tanks into this picture, no such thing. Okay. So, because of the presence of this free surface effect, the shape of the water line is something like this. So, the water line WL is no longer a straight line, as we will see in the case of a in all our problems so far. Of course, if you have a very calm ocean where there is no wind, probably let us say that we remember we talked about stability regulations in we talked about stability regulations, and we saw that the there are coastal regions where the winds can be as low as some not coastal, let us say that even in the open ocean there are regions where the winds can be as calm as probably 10 knots. 10 knots is 5 meter per second, that is fairly low wind, and even in such cases the elevations might be very small in terms of few centimeters, it is very less. That is almost a almost a straight line. So, in those conditions we can consider the free surface to be a straight line, the water line to be a straight line, but in other cases where in reality when you go to open oceans where the winds are in excess of 20-30 knots, or even in coastal oceans, definitely coastal regions is highly more prone to waves. So, when you study the wave height in coastal areas comes to 1 meter or 1.5 meters, it can be very high, as high as that, and you in such that is in an ordinary case you have about 1.5 meters wave height. Now, these waves the presence of waves produces a water line like this. Now, this is the presence of water line, this is the therefore, this is a new type of water line that we are going to address in this kind of problem. You will see that when you change the water line into such a wavy form, there are effects of that on the different stability calculations. The problems become different. Now, there are in general now see there are in general two types of waves, two types of scenarios associated with waves and ships. I mean the effect of waves on ships is two. There are two extremes that we consider. First is this is one case, that is we assume, I am going to assume here that you know the basics of waves. By basics of wave I mean things like the crest of a wave, the trough of a wave, wave height, wavelength, wave time period, wave frequency, etc. So, these are very basic things of waves which are usually taught in the probably in the 12th standard. So, or maybe even the first year of B.Tech. So, by now you should have some idea of what are waves. We are not going to do that, I am not going to do that, it is too elementary. So, I going to so this is the crest of a wave. Now, assume that the crest of a wave occurs at midship. So, this is a midship, now means the exact middle of the ship, and at that point you have the crest of the wave. So, the crest of the wave is occurring at midship. This is one possibility, one extreme scenario, and another possibility is when you have the trough of a wave, the other possibility is when you have the trough of a wave occurring at midship. So, this is case 1, this is case 2. Now, two possibilities exist when you have the crest of a wave existing at midship. So, as you can see, as you can imagine, the wave is like this, the ship is on top of that wave, and so the wave is like this, the ship is lying on top of the wave, the midship of the ship, the midship portion of the ship, the center part of the ship, the exact midship section, that cross section is exactly staying on top of the crest, and the second case you have the wave is like this, and the midship section is lying on the trough, and the wave is like this, okay, the wave occurring, and the midship section is occurring on the trough. Now, these are two extreme cases, and you will see that when you study these two extreme cases, you are in fact considering all the possibilities, means you are considering the extremes effect of waves on ship. So, if you assume that the presence of crest, there is some effect of stability, there is some effect of wave on stability. In the second case, when the ship is on a trough, you will see that the extreme opposite possibility of the effect of wave on ship occurs. So, these are two extremes. So, you study these two extremes, every situation in between where you have the wave occurring somewhere in the ship, means occurring along the ship, you will have it will be somewhere in between these two extremes. So, between the crest and between the trough, if you have now this kind of wave where you have the trough this is known as a sagging wave, sagging condition. The ship is in a sagging condition. So, as you can see, the ship is like this now, ship is lying on the trough. So, ship is ship is being bent like this. If you consider ship to be a beam, simple beam, ship is being bent like this, this produces a sagging condition. And in the other condition, when the ship is, the center of the ship or the midship section is lying on the crest, the ship is like this. So, if you consider the ship as a simple beam, the ship becomes like this. It is in a, we call it in a hogging condition. So, these are two extremes of the waves. So, the ship can either be in a sagging condition or in a hogging condition. So, the ship is bent like this or the ship is bent like this, two particular cases when the because of the shape of the wave. So, these are effects of the waves on ship. Now, we will have to see how this will change the different parameters of the ship, how it will affect the GM, for instance the metacentric height, maybe the BM, how it will affect the virtual weight of the ship itself. You will see that the virtual weight of the ship, which we will see again, it is coming, the virtual weight of the ship, which is the apparent weight that the ship feels in the presence of a wave, means in on top of a wave, for instance, the ship in fact has a tendency to feel less weight than its real displacement. It feels less weight. There is some extra force acting which tends to reduce its weight, and in the presence of in the crest, in the trough, for instance, the ship will be producing some extra forces, as a result of which it will tend to become heavier than it really is. So, it will appear to be regular, it is not heavier than it is, but because of an extra force acting, it will add to the displacement, and the total displacement seems to become more than its real weight. So, these different conditions exist because of the presence of waves. So, these have to be studied in detail, because as you can imagine, the ship is mostly subjected only to such wavy water lines. Ship is very rarely subjected to the very straight horizontal water lines, and of course, it is a fact that we this wavy water line or the curved water line is important only in terms of the length of the ship, means only in the longitudinal direction. So, it is only the longitudinal analysis that is mainly affected by waves. Why? Because the wavelength is usually of the order of, it can vary, of course, wavelength varies a lot. I mean, for a tsunami it can be as high as 100 kilometers, but we are talking about ordinary free surface waves. They usually have a wavelength ranging of the order of the length of the ship, 100 to 200 meters. So, if that is the length of the wavelength of the ship, when you are considering the transverse direction like this, which is the breadth of a ship, let us say it is 5 meters or maybe even 10 meters, even if it is a large ship, the breadth might be even 10 meters. So, even a distance of 10 meters, this waviness, maybe it will go like this, and it is like this, and then slowly it goes. So, this variation is much larger than can be seen in a breadth as such. So, the breadth you really do not discern that difference, the wavelength difference is not discerned so much. So, we do not really bother about so much about waves in the transverse stability analysis like GM, KM, etc. So, it is not that important, but it is very important in the longitudinal analysis, because longitudinally you will see that the wavelength is not at all a straight line, wavelength is a curved surface. It is very important that you consider the curved nature of the surface if you are considering the longitudinal section of the if you are considering the longitudinal or the shear profile of the ship. So, in that section when you are considering the longitudinal bending, it is very important that you consider a wavy profile. So, so what we are going to do next is we are going to consider the longitudinal analysis. Before that, when you have this longitudinal in the longitudinal direction, we say that the wavelength of the wave is the same as the load water line, length of load water line. So, what we say, the meaning is this: So, what we are saying is that this length, let us assume that this is the load water line, this is the horizontal load water line or the plane load water line without the wave. Now, let us consider a sagging wave. Therefore, in a sagging wave, what we have here, this distance, you know that you have to know that the distance, this is a sagging wave where the wave trough is exactly at the midship. So, this is the crest. So, this is one crest, this is another crest, two crests are occurring at two ends of the ship of the load water line. So, this is the load water line, and this is the length of this is known as the length of load water line or LWL, length of water line. Now, so what we are going to assume in our analysis is that the length of the ship, length of the water line is equal to the wavelength. So, you know that wavelength is defined as the distance between two successive crests. This is a crest, this is a crest. So, this distance LWL, the distance of the water line, the length of the water line is the distance between two successive crests, and you have the trough at the midship section. So, this gives you this is the condition that we are going to study. Now, you will see that when you are trying to analyze waves, we can have different types of waves. I am not talking about the physically, you can mathematically, when you are trying to simulate waves, you can define different types of waves. The simplest of those waves would be a sinusoidal wave, a sine wave or a cosine wave. So, these are sinusoidal waves. Another type of waves which are usually used is known as a trochoidal wave, and these kind of waves have found much application in naval architecture, mainly because of their resemblance to the exact type of waves that are found in the ocean. So, it is mostly that the ocean we consider trochoidal waves. Trochoidal waves so first, before we go into the analysis of the longitudinal section of the ship, we will see what is meant by a trochoidal wave and what is the mathematics associated with a trochoidal wave. So, this is the so we have what is called as a trochoidal wave. Now, we will have to define the what is a trochoidal wave. Now, trochoidal wave is defined like this. Suppose you have a straight line and suppose I have a circle here. Suppose you consider a point on the circle and the circle rotates like this. Let us assume that the circle rotates like this. It just rotates and it moves. So, moves on the underline on this under part of this straight line. So, it is like you are considering a ground and a ring is rotating on the ground and just rolling like this. It is moving like this and it is rotating. So, it is rotating like this and it is moving like this. So, it keeps going like this in this direction, it moves in this longitudinal direction along the underside of the straight line, and when this happens, the trajectory of this particle, it traces out a path. So, the trajectory of this particle traces out a path. This is a particle we are concerned about. It traces a path and that path is what produces a trochoidal wave. If that path is trochoidal, that is known as that is the trajectory or the locus. Locus is what we call as a trochoidal. So, that is what we are going to define now. Now, let us assume it is like this, we will draw it slightly bigger. So, this is it, this is the circle. Now, we are considering a particle here, and so this moves through a distance x, and so it comes here, it becomes here. The same ring or the circle has rotated or rolled by this much distance x. The center, okay, the center has moved by a distance, this is the center, the center has moved by a distance x, as a result, and in the time that the center moved a distance x, this particle is initially here, p0 is the initial position of the particle and the particle is now at p1. So, in the time that the circle moved a distance, circle horizontally moved or translated a distance of x in the horizontal direction along the underside of this, the particle p0 reached a point p1, it moved an angle, let us say theta. So, what we have is that as the particle moved a distance x, the it moved through it rotated, the particle rotated through an angle theta. Now, what we say is that let us suppose that now we are going to define the problem such that a trochoidal wave is defined like this. So, a trochoidal wave, in a trochoidal wave we say that as the circle moves through a distance, as the center of the circle moves a distance of lambda, which is the wavelength of the wave, okay, wavelength of the trochoidal wave is lambda. So, as the circle rotates through a distance of lambda, as the circle translates through a distance of lambda, the particle rotates through an angle of 2 pi. So, by the time it moves lambda here, it rotates through 2 pi completely, it starts from here and reaches back there, that is 2 pi. So, when it moves a distance L, or in this case we will call it as lambda as the wavelength, it rotates through an angle 2 pi. Therefore, when it rotates through an angle theta, it must have translated by a distance of lambda by 2 pi into theta. Okay. So, this is the distance through which it would have moved, x will be equal to lambda into theta by 2 pi. So, this is first relation that governs how the particle tilts. Now, in this note that the distance between the height of the wave, what we mean as the height of the wave is the distance between the crest and the trough. So, if you consider the crest of a wave, in case of a sinusoidal wave you will see that the crest of the wave is at an equal distance than the trough. In this case also it is true, in trochoidal wave also it is true, you will have the crest and trough at equal distances from the still line, now still water line. So, in this case you will see that the height of the wave is equal to the height of the wave you see here is equal to h, which we call it as, it is equal to 2 r, where r is the radius of the circle, this circle. So, this is the circle, this distance is r. Therefore, this is r, another r, because the particle always goes like this, particle can never move a distance greater than r, because the particle is moving along the circle, and therefore, the particle can always move a maximum distance of only r from the center, this is r. So, r plus r, 2 r gives you the height of the wave, that is the distance through which the wave moves maximum. Now, how do we find the position of the, how will you get the x coordinate? X coordinate at any center is given by, the x coordinate of the particle at any point is given by this x, which is the distance through which the center of the circle has moved, x minus this distance, We are talking about the position of the particle. Note a particle is actually this p, it is a particle that is moving along the circumference, it is not moving, we are not bothered about what happens at the center of the circle, the particle is moving along the circumference of the trochoidal wave, and therefore, the distance through which the particle has moved is x at any instant is x, which is the distance through which the center has moved minus this distance. So, that will give you the distance through which this distance through which the particle has moved, this distance. So, you get this distance through which the particle has moved. So, that is x is equal to, let us call it x prime, it is equal to x, that is the distance moved by the center minus r sin theta, just this. So, r sin theta minus, so this will be, so if this is theta, this distance will be r sin theta and this distance will be r cos theta. So, you can look at it like this, it is probably easier. So, this is theta and this is therefore 90 minus theta. So, this is r sin theta. Therefore, therefore, this distance becomes r sin theta and this distance becomes r cos theta. Oh, sorry. This distance becomes r sin theta and this distance becomes r cos theta. Okay. So, therefore, our distance through which the center of the distance through which the particle has moved horizontally is x minus r sin theta. Now, x we have seen here is lambda by 2 pi theta minus r sin theta. So, this gives you x prime, the horizontal distance through which the. So, this gives you the x at any instant of time for the particle, the x coordinate of the particle at any instant of time, provided you fix some origin. Now, the best way to fix the origin is, suppose you are considering the ship in this case. Now, so here you have the ship. So, this is the water line and you know that your, let us consider a sagging wave in all cases. So, this distance let us fix at the origin always, this is always fixed as 0 0. Therefore, here x is equal to 0 and you are talking about this position at any instant of time p, which is we are talking about the p's. Right now, we devise the relation for the x coordinate. It is very easy to get the, let us call this the z coordinate, this is z and this is x. You know y is in the transverse direction, that does not come in the picture as such, because it is a we are talking about waves in the longitudinal direction. Transverse direction is, let us assume it is horizontal for that matter, for the reason I described before. So, this is x prime, this will give you the x coordinate. Now, the z coordinate is very simple, it is r cos theta, I have already shown you that, it becomes h by 2 cos theta. Now, once you have this x and therefore, once you have this x and z, you are getting at any so at any x and z you can with any particular value of x and z you can draw the curve, means at any point if you have the x and z, how will you solve this as such? I will tell you that. That is what we could do first is you take the ship, okay. So, you take the ship and first of all you draw the stations. So, let us assume that this is the aft perpendicular and this is the forward perpendicular. What we will do here is, we can, I make a slight difference from the previous statements. What we could do is, let us assume that instead of LWL equal to lambda, this time we will assume that LPP is equal to lambda. LPP, as you know, is the length between perpendiculars. So, we are again going to consider a sagging wave, where that means you will have the trough of the wave at the midship. Now, what that implies is, we will first set the crest, one crest of the wave at the aft perpendicular, the wave will proceed, the center of the trough will come at the midship, and again the next crest of the wave will come at the forward perpendicular. So, like this. And so, this is the length between length between perpendiculars is equal to lambda, the wavelength of the wave. Now, what we do next is divide the whole ship into a fixed number of stations. Let us assume we divide it into 10 fixed number, let us say 10 stations. So, like this you divide it into stations. So, this we will call it as station 0, station 1, station 2, like that it becomes station 11. So, you have 10 fixed 10 intervals or 11 stations. So, you have 11 stations and 10 fixed intervals. Oh, this will be station 10 because 0 to 10. So, you have 11 stations and 10 spacings. And so what we have done is the whole region of the, so the whole lambda, the wavelength of the wave, we have split it into 10 spacings. So 10 spacings, we have split the whole ship into 10 spacings. Now the next step is, we have already got these expressions, x is equal to r theta, x is equal to lambda by 2 pi theta minus r sin theta. Now we have this expression. Now where is equal to h by 2, we have already seen r is equal to h by 2. Now now this h, that is the wave height, is a property of the wave that is being studied. In general, you will see that when you are doing ship analysis, you come across waves that have of an order of LWL or LPP divided by 20, that is roughly the range of h, the height of the wave. So of course, if you are really doing an analysis, you really need to know what is the height of the wave, the exact value of the height of the wave. But since right now we are doing, we are just expanding on the theory, we will say that the height of the wave, that remember, that is something you have to be given. You cannot guess the height of the wave, that is no such thing. You, whatever method you have, you run some numerical wave models, some model, and you develop the height of the wave as a result, or you measure the height of the wave using some tide gauge or something. And once you have the height of the wave, you will get the h, you will get this h, the wave height. So here what we have is x is equal to h by 2. In this case, we can assume, for instance, it is LPP by, roughly this is the order in which you will be seeing this wave height will be about the wavelength of the wave. Now as you can see, LPP is equal to lambda here, the length between perpendiculars, we have set it equal to lambda. So roughly h is equal to lambda by 20. Now okay, so x is equal to lambda by 2 pi, and again we have everything here. Now x, what is x? X is this, now x is this distance. So let us consider the station 1 now. Station 1, you know what is x, this is your x. It is the position of your first station from the 0 water line, 0 station, that is from the aft perpendicular. From the aft perpendicular, what is the position of your first station, that is distance is this x. So let us call it x1, x of station 1 is equal to lambda, again is the distance between perpendiculars. You know the length of the ship, I mean of course you have to know what ship you are dealing with. So you know the length of the ship, this divided by 2 pi into theta minus h is LPP by 20 by 2 into sin theta. So you end up with this x1, we know this is the some value, the distance which is actually equal to, in this case, LPP by 10, means the total length of the ship we have divided into 10 spacings by 11 stations, we have divided into 10 spacings. So LPP by 10 is equal to x1 is equal to this equation you get. Now in this equation, the only unknown that you have is actually theta. So of course it is a slightly transcendental equation, it is not directly solvable because you have theta here and sin theta here, but it can be solved using iterative method like Newton-Raphson method and all that. You can use that to solve it and you will get theta. Okay, you solve for theta. Once you have theta, now therefore remember this is the value of theta, or this is the angle through which the particle that is travelling along the wave has rotated when it has moved some distance x. Now how do we find the vertical distance z through which it has moved if it has rotated through an angle theta? It is very simple. We have the formula z is equal to r cos theta equals h by 2 cos theta. Therefore, you have z equals h by 2 cos theta. Now h is known, LPP by 20 into cos theta. Theta you just measured using the theta you just calculated in the previous section. So there you have z. So like this we have for the first station, like so. Now this one, for this particular x you have this position. So you know what is the z that we have measured? This z is actually this is the z that you have just calculated. This z means it is the vertical distance through which the particle has moved as a result of the wave translating a distance x. So this gives you the x and z of this point of the wave. Similarly, you take the next point x2, station 2, you will calculate the z like this, here you will calculate the z. So, with these different values of x and z for different stations, you can calculate the wave heights or the wave profile. So, as a result of this calculations, you will now end up with the proper wave profile, and the wave, remember, we have defined such that you will get it, it is defined such that the center of the wave, the center of the ship, the midship will have the trough on it. So, this is LPP, this is the aft perpendicular and this is the forward perpendicular. So, you have the aft perpendicular and the forward perpendicular, and here you will have a crest, here you will have a crest, here you will have a trough, and you have all these z's, you have the z at each station, and as a result you have the complete wave profile, you have a complete sagging wave profile. So, you have the sagging wave profile. Now, this will give you the trochoidal wave, you will get the trochoidal wave on the ship. Now, we have the, right now what do we have? We have the profile of the we have now the profile of the wave superimposed on the total length of the ship. That is in fact the one very important way of this, one of the important things in doing this. So, now you have the wave profile, and based on this we can calculate the longitudinal now. Right now, we have the we have the wave profile. Now, how do we find the mean position about which, now the of course, the circle is rotating about that center, and the as a result you are getting the wave. Now, there is a region, there is a line in between the trough and the crest of the trochoidal wave, and such that if you take the integration of, let us take one wavelength of the wave, if you integrate the wave over one wavelength, you will see that the total area comes to 0, means. So, if you consider this to be that line, in the case of a trochoidal wave, it does not, in the case of a sinusoidal wave for instance, let us see, wait. So, first of all, so we are considering a trochoidal wave here, and what I am saying is that if this is a point which will I call it as some still water line, and this is the center over which the circle rotates, this center is given by z equal to 0. Okay. Z equal to 0 is the point over which the center of the circle moves, and the circle I am talking about is the circle over which the particle is rotating. So, particle is rotating like this and the center is moving. That line which is traced out by the center is this line, it is z equal to 0. Now, in case of a trochoidal wave, you will see that if you take an area, area means this is a positive area and this is a negative area. I am talking about area about this point, about the z equal to 0. If you take area about this, this is area. If you sum up this area and this area, I mean this area and over one whole water length, if I sum up this area and this area, it does not come to 0, because it is not symmetrical about this z equal to 0, the trochoidal wave. On the other hand, if you have a sinusoidal wave, then it will be, if you take an area, let us consider a sinusoidal wave like this. This is one full wavelength. So, it is started from the center and ended at the center. Now, if I take the whole area, this area will be positive, this area will be negative, this area and this area will cancel out each other, and therefore, the total area comes to 0. Now, in trochoidal wave it is not at the center, but it is at a distance. In trochoidal wave it is at some point z equal to a, some distance away from the z equal to 0. How do we find this? This is the easiest way is you use z minus a, the total integral between 0 to 2 pi, 0 to 2 pi of dx is equal to 0, where dx, best thing is x varies from 0 to lambda, the wavelength of the ship, wavelength of the wave. So, z minus a dx between 0 to lambda is equal to 0. This is the Now, the first one 0 to lambda z dx can be written as, that is, you know that by the time that the wave center moves through a distance of lambda, that center when it has moved lambda, the theta has moved through 2 pi. Therefore, integrating between 0 to lambda of dx is the same as integrating d theta from 0 to 2 pi. It is the same time, it is the same instant. So, 0 to 2 pi. So, z we have seen is r cos theta into what is dx? We have already seen what is x. Remember, this is the expression for x. You just differentiate this, dx will give you lambda by 2 pi into d theta, lambda into 2 pi d theta minus h by 2 into cos theta d theta. Therefore, r into lambda by 2 pi minus r cos theta into d theta. Now, just integrate this whole expression. So, this is z, and the second this is this one, and the second one is just this one is just 0 to lambda a dx, which is very simple. You will not have this term. So, 0 to 2 pi, r cos theta is not there, just lambda by 2 pi minus r cos theta into d theta. Now, if you integrate the whole thing, and if we set this means the total area equal to 0, you will see that you end up with A equal to minus r squared by 2 into lambda by 2 pi. So, this is your value of A. So, this is the center about which the total area under the curve will become 0. So, this is the expression for trochoidal wave, and so this is the trochoidal wave that is mostly adopted in naval architecture studies because of its proximity to the real type of wave found in the ocean, that free surface waves are very close to trochoidal waves, and therefore, the concept is, and it is easy to do this calculation as well. It is more accurate also than the sinusoidal waves, and so therefore, we follow this. And then couple of points is that just like any type of waves found in the any other type of wave, you will see that in a trochoidal wave now see, first of all, when you have the surface, there will be some waves that are traveling in this circular in this, we have seen it is moving in a circle, this particle is actually moving in a circle, and it is translating like this, and it is moving in a circle. And so, below that there is a first circle. This wave does not really completely stop here, that just below this also there will be another wave, there will be another thing moving in another circle, another particle moving in another circle, here another circle, it moving like this, below that another circle, and like this it keeps continuing going down, and the end result is that you have a series of circles going down, and you will see that as you progressively go down, the radius of this circle will keep decreasing. So, the radius actually exponentially decreases with depth. You will see that the radius is given by, so h by lambda by 2 pi. So, h is the water depth through which the h is a water depth through which the center of the circle. So, if h equal to 0, then you have the first one, that is at the surface, h keeps increasing, you have the water particles as you going in a circle as you go down. So, you will see that as you keep going down, the radius of this circle through which the water goes, that water rotates, that radius of that circle actually keeps coming down exponentially. So, that is the first thing. Then there is another concept which we call as virtual gravity. I already mentioned this, that is that as you can see, as the particle is going in a circle, that particle has two forces acting on it. First one is the weight of it, mg, the mass into gravitation acceleration, m into g will be acting on that particle, that is directly downwards, and since it is moving in a circle, there will always be a centrifugal force acting on that particle. Now, centrifugal force is given by m omega square r, m omega square r, where omega is the angular frequency of this rotation. So, r is the radius of the circle, m omega square small r, and now this will be like this. So, So, this particle here it will be subjected to mg minus m omega square r, because this will be acting outward like this, and if the particle is at the bottom or at the trough, it will be subjected to mg plus m omega square r. I hope it is clear why it is plus and negative, because here always centrifugal acts outwards. Here when it is acting outward is against mg, here when it is acting outwards it is augmenting mg. So, mg plus m omega square r. So, these are, so what you see here is this additional thing actually seems to augment the gravitational force, or it either decreases or increases the gravitational force. That is what we call as virtual gravity. There is a slight increase or decrease in weight from what is normally seen. So, what is its original? So, if you have a body floating on that, it will be subjected to this mg this centrifugal force will either increase or decrease its weight. It is seen to increase or decrease its weight, and therefore, on the surface when it is on the wave crest, so when the particle rides on the wave crest, you will see that the so when the particle rides on the wave crest, the weight of the ship is seen to be decreased. So, as you can see that minus comes, its weight is decreased, and when the ship, so the ship will seem to be tender, that is the word, we say that the ship becomes a little tender at the wave crest, and when the, on the other hand, when the ship is on a wave trough, on the other hand, the weight is augmented and the ship is seen to become more heavy than it really is. So, on a trough the ship seems to become heavier than it really is because of this additional centrifugal force which augments the weight, and this. So, there are two principles mainly associated with trochoidal. So, first thing you have to remember is that the ship analysis is mostly done using trochoidal waves, and not, of course, the lot of applications using sinusoidal waves are also there. It's not excluding that. Of course, most of them are done using sinusoidal waves only, but trochoidal waves is a very important phenomenon that is used mostly in these longitudinal studies, and this is what we really mean by a trochoidal wave, and these are some of the properties of trochoidal waves. And in the next class, I will talk about some of the applications of trochoidal waves and longitudinal bending on the properties of the ship, on how we calculate it. Okay. Thank you. I will stop here.